Okay, so last part of the notes here. Last part of the notes. Let's do baby poop brown. Alright, so this last little bit is more so one of a drawing that we'll do, and this is how we collect gases over water. So this is something, every once in a while they'll ask you about how to proceed, how to do a lab, like what procedure would you use and so on. So this is one of those things that they've asked before, and this is also a lab that we'll be doing probably this week, although it's really cold right now, the water is, so I don't want to do it until maybe Friday if it warms up then. Because you're going to have to stick your hands in cold water. Yeah, and right now that just sounds painful to me at the moment. Okay, so the water displacement for gas collection. Does this color show up okay? Yeah. So this is the last little section. So water displacement for gas collection. I'm going to draw a beautiful picture here, okay? So here is my Bunsen burner. And we have a test tube. I think I drew this for you guys, didn't I? And we have a tube in here. I believe I did. And there is stuff down here that you're heating or doing something with, and you're producing gases, okay? And so you're going to collect the gases, and it's going to go out a glass tube in through water. Yeah, did we do this already? Did I at least talk about it? And what you have in this case is a udiometer, which is what we're going to use. And you have you have water up in here. Okay, and I'm going to draw this with a pencil in here. You've got this filled with water. You've got it totally filled with water. And as this thing bubbles up, it collects the gas, and the gas displaces the water. So you guys get that concept, yes? You fill it up with gas, you push the water out. So that's called gas collection through water displacement. Since the gas is collected over water, there will be water vapor mixed in with the gas. Water vapor is just gas. So what you have to do is you have to use that law of partial pressures. And so the total pressure, and it's really cool how you get the total pressure, it's really simple too, will be the water vapor plus whatever gas that is you're collecting. So what's cool about this is in order to get the air pressure inside there, what you do is you move the tube up and down so that the water line inside the tube is equal to the water line here. If the water line inside the tube is equal to the water line here, then it's the same pressure as what's outside. The pressures are the same inside the tube and outside the tube. So all I have to do is look online and say, hey, what's the air pressure today in Borger? And that'll be the air pressure. So it's really kind of cool. Water displacement for gas collection. This pen's kind of small, isn't it? No, it's not that bad. Yeah.
Yeah, they're very defined too.
Yeah. So since the gas is collected over water, you're going to have not just the gas you wanted from this chemical reaction, but you're also going to have some water vapor in there. And it's enough that it makes a difference. We wouldn't even have to do a chemical reaction. I think what I'm going to have you do is we have some butane lighters, and I'm going to have you stick your hand under here, and you're going to just push the nozzle on it, and it's going to put gas up in there. But you're still going to get gas, water vapor pressure inside there, so it works really well here. The total pressure is usually the atmospheric pressure that day. Or if instead they've just got the setup and they're saying, hey, here's some information, they'll tell you in the diagram. So it could be or what's on the diagram, the drawing that they give you. It just depends. Once you know the pressure, then you can do PV equals nRT to find the moles of gas. And the volume, I'm going to slide this back down a minute. The volume you get from here, because the tube we're going to collect it in, that udiometer, is going to give you a volume. So you've got the volume. You can read the volume in the chamber here. You've got the pressure. You've got it there. So now you can use PV equal nRT. So once you know pressure and volume, you can use PV equals nRT to find number of moles. Remember, if in doubt, always look for number of moles somewhere. Always, 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 always. Look for number of moles. Once you've got that, grab a calculator. Okay, so again, there are two major equations that you're dealing with. Two major equations. You've got the combined gas law. You guys listen up. Combined gas law and ideal gas law. Combined gas law, remember, it's the one where you have a gas and you're messing with something in there. Changing the pressure, changing the temperature, changing the volume, but you've got one gas, there's no chemical reaction going on, you're just messing with crap. The other one is the PV equals nRT, the ideal gas law. This is when you have everything but one piece. PV nRT, you always got R. It's going to be it's a given, right? It's a constant. But P, pressure, volume, temperature, something's missing. A lot of times we use this one if there's a chemical reaction and we want to find number of moles. But the easiest way to tell which one to use is if you've got two volumes, two temperatures, two pressures, then more than likely you're going to be using the combined gas law. So flip over to page number 11 in your packet here. Page number 11. And I'd like to point out a couple of things. You can read through that on your own, but right down here, again, it's pointing out that there's more than one unit of measurement for pressure. On the AP test, they are very specific. They don't use kilopascals, but they use millimeters of mercury and torr. You can swap out. Those are interchangeable, torr and millimeters of mercury. Pascals and kilopascals are also on the list, but it just depends on who's writing the question, what unit of measurement they use for pressure. So you got to pay attention to that. A sample of SF6. What is SF6? What's the name? Yeah, sulfur hexafluoride occupies a container of variable volume. All right. Here's the first phrase you need to be aware of. The volume can change. You're not keeping it constant. Think of a balloon. Can't you change the volume of it? That's the easiest thing. Always think of something that you've got experience with. If the sample originally occupies a volume of 50 mils at 755 millimeters of mercury, calculate the pressure which must be exerted to lower the volume to 25 mils. Okay. Your best thing to do always is make a list of what they gave you. Go through here, circle your numbers. You've got 50 mils, and notice that these two go together. So I've got a volume and a pressure, and then I'm going to change things, right? So this indicates to me that I'm going to use the combined gas law. Okay, so my combined gas law says, and I like to write the equation out too, P1 V1 T2 N2 equals P2 V2 T1 N1. Is that on your green pages anywhere? It's not, is it? Okay, there's another way to write this that might make it easier for you to remember. If you have P1 V1 over T1 N1, all the ones are together, or you have P2 V2 over T2 N2, whichever makes it easiest for you to remember, whichever one you like. I know a lot of people like this one because there are no fractions. It just depends on what you want to do, but you're going to have to know that. So I'm going to say the sample originally occupies a volume. So here is my V1. V1 equals 50 mils. And that means here's my P1, and that's 755 millimeters of mercury. Calculate the pressure, so they're asking me for P2 to lower the volume to 25 mils, and here's my V2. Here's the beautiful thing about the combined gas law. Did they say anything at all about temperature? No, then we can cross it off. Did they say anything at all about number of moles? Nope, cross it off. So your equation becomes P1 V1 equals P2 V2. Yeah, see, it's glorious. It's one of the easiest ones to use. I like the gas laws problems because they just make sense, and they're simple and easy. The key here, I can't emphasize this to you enough, guys. And I know some of you guys, for some reason, have this reticence about writing things down. It didn't take very long to write that down at all. And when you write the stuff down, then you can see exactly what it is that you need on here. Okay? So I just plug my numbers in. P1 is 755 millimeters of mercury. I like putting parentheses around it because you need to put your units of measurement, make sure you've got everything straight. V1 is 50 mils equals P2, we don't know what that is, times V2 is 25 mils. Notice I've got milliliters on both sides. I'm going to divide it out so I know it's going to cancel, and my only unit of measurement left over is the millimeters of mercury. Pop that into your calculator. I would do that if I had a calculator. So you have a pressure 2 of 1510. What's the unit of measurement? Okay, take out your PTV card. Yeah, PTV card. Okay, again, really simple, straightforward conceptual thing. So we took the temperature at the same. They didn't say anything at all about temperature, right? So we basically took the temperature at the same. So we turn on temperature. And what did we do to the volume?
The volume went down.
We decreased it. So when the volume went down, what happened to the pressure? Yeah? Again, it only works, this little card is just a visual thing. It only works if you have one of them that's held constant. And it only works with your, typically with your combined gas law. So it shows you what that is. Flip the page. Okay, so again, this is one of those where we can talk about the temperature. You can have a viable temperature of 0 degrees Celsius, which would totally screw everything up, wouldn't it? So you can't use Celsius. You have to use Kelvin. So any problem using gas laws has to have that temperature in Kelvin. So a 545 ml sample of nitrogen gas initially at negative 220 Celsius is heated to 100 degrees Celsius. Calculate the new volume, assuming the pressure does not change. Okay, so your first step, I know it's going to be my combined gas law, right? I like writing the equation P1V1 T2N2 equals P2V2 T1N1. The T's and N's are together, the P's and V's are together. Look at this. If you have your PTV card, the P's and V's are the ones, the T's and N's are the twos, yeah? Okay. So my next thing is I'm going to go through here and I'm going to write my givens. So I've got a sample of nitrogen originally at negative 220. So I'm going to put these two together. So I've got my volume is 545 mils and my temperature is negative 220 Celsius. I heat it to 100 degrees Celsius, so now my T, those are my ones, my T2 is 100 degrees Celsius, and they're asking me to calculate V2. I cannot leave it like that. I have to change it to Kelvin. So the first thing I'm going to do here after I've got my givens down is I'm going to change this to Kelvin. So 273. So I've got 53 degrees Celsius, Kelvin and 373 Kelvin. You have, if you don't change it to Kelvin, you're not going to come up with the right answer. It said that the pressure stayed constant, so I can cross off my P's. They didn't even mention number of moles, so I can cross that off. So I've got V1, T2. Pay attention. Volume 1, 545 mils. And temperature 2, 373 Kelvin. You got to pay attention to that. Volume 2, that's what they're asking me to find. And T1, here's my temperature 1, 53K. Notice my kelvins are going to cancel out because I'm going to divide out the 53K, and all that's left is my mils, so my volume is going to be in mils. They may ask you for the volume in mils. They may ask you to find it in liters. Doesn't matter. Okay, what kind of volume did you get? In the 3000s?
1,835 milliliters or 3.84 liters.
Milliliters, right?
Yep.
How many sig figs should I have? 3, so 3,840
Yep.
mils. I don't like that. I don't. I hate it when they do that, but that would be something. Okay, one more and we'll stop this part of the video and you guys will be doing some of your stuff on your own, maybe. Okay, so number 3, calculate the volume of a sample of helium at negative 33 degrees Celsius in 1.23 atmospheres if it occupies a volume of 2.34 liters at 54.5 Celsius and 1026 millimeters of mercury. Okay, so notice they're giving you 2 temperatures, 2 pressures. Okay, so we know it's the combined gas law. So P1V1 T2N2 equals P2V2 T1N1. Yeah? And let's write our stuff down. Let's see, calculate the volume of a sample of helium at, here are my numbers right here. So I'm going to call that volume 1. Doesn't matter what you call 1s and 2s as long as they're consistent with each other. So volume at negative 33. Oh, wait. I didn't read the whole question. They've given me the volume, haven't they? If it occupies, oh, wait, no, they didn't. Calculate the volume of a sample. All right, I'm doing it right here. Negative 33, so T is negative 33 Celsius. And P1 is 1.23 atmospheres. If it occupies a volume of 2.3 liters, V2 equals 2.34 liters at 54, so T2 is 54.5, yes? And pressure of 1026 millimeters of mercury. What's a problem?
We to translate them to Kelvin.
Okay, so one, change them to Kelvin, and what's the other one? Millimeters. Notice our pressures are different. So we got to do two things here. So the easiest thing is let's change our temperatures to Kelvin. So negative 35. What is that? Oh, it's 33, isn't it? 204?
Yep. No, take one.
Oh, that's because I did it backwards. 240. Geesh, I put 37 instead of 73. And then, is it 54.5? Did I write that down right? Okay, so do we want to change the pressure to atmospheres or the atmospheres to the millimeters of mercury?
Isn't it atmospheres to the milliliter?
Okay, so here's why I like changing it to millimeters of mercury, like changing it to atmospheres. Notice the numbers for atmospheres are smaller
Yeah.
in general than the millimeters of mercury. So for me, it's easiest to, you won't get it wrong if you do it either way, but I like to change it here. So if you look right here, 1 atmosphere is 760 millimeters of mercury. So if we want to change this, I've got 1026 millimeters of mercury. So for every 1 atmosphere, there are 760 millimeters of mercury. So basically divide by 760.
1.35.
Did you guys see how I did that? It's just like changing feet to meters, or feet to inches, or something along those lines. Do I need this? Do I need to show that again, where it's not kind of framed up in there? Yes or no? No? Nope. Okay. All right. So now plug your numbers in. Do we have anything to do with moles? No. So we can cross the ends off. So P1. V1, we don't know what that is. T2, P2, V2, and T1. You have to make sure that you get the right T's with the right stuff. Those numbers in right.
Don't we have 3 sig figs?
1.23. I'm seeing 3 sig figs, yes. 327. 1.35. Yep. 2.34. And 240. I got 1.89. No, 1.88. Yeah. Did you guys get that? Yay or nay?
No.
Okay, pop it in again. So when I put this in, I put this in first and put a big parentheses here and here. Divided by, open my parentheses here, close my parentheses here. I only put parentheses around each section here simply because it kind of keeps them as a separate unit for me. You don't have to. I like to do it because it keeps them distinct. I don't put all those parentheses in my calculator. I only put the yellow ones in the calculator.
1.83?
Uh-huh.
Okay.
Nope.
Okay, did you put in open parentheses? 1.35 times 2.34
Yeah.
times 240,
Oh, I switched up my number.
the temperatures.
Liters?
Okay, so if you look, notice this, the atmospheres are on both sides, so they're going to cancel. and the K's are on both sides. They're going to cancel. The only unit we have left is liters. So it's going to be liters. Okay, and let me turn this off for just a second.